A starship crosses the dark between suns, engines silent, its target locked, gliding toward a new world. That is the image. Here is the problem. Reaching another star was never the hardest part. Staying in a machine that still works when it arrives, that is what almost nobody survives. Out there, no one can fix you. No spare parts arrive. Every scratch from a speck of dust, every particle of radiation, every frozen circuit is permanent, and it all adds up across centuries. The ship might reach its destination exactly on course, right on schedule, and still arrive blind, powerless, unable to slow down. A perfect corpse, gliding past a world it can no longer see. So how long could a real starship actually survive out there? Let us find out. If you find this kind of question as fascinating as I do, the strange, quiet engineering of survival across the stars, I would be grateful if you tapped like and subscribed. It really does help this channel grow. Now, get comfortable, settle in, and let your curiosity wander a little. Let's begin. The ship lets go. For years it has been climbing. Building speed, shedding stages, pushing away from the warmth of home until the planet that built it is only a bright point behind it. And then, not even that. And now, at last, the engines fall silent. There is nothing left to burn and nothing left to push against. The ship is simply moving, coasting through a darkness so complete that its destination is still years away, even at the speed of light, and far, far longer than that for anything human hands have ever made. This is the moment we picture when we picture a starship. The leaving, the great escape, a sleek machine slipping free of the solar system and setting out across the void toward a new sun, carrying instruments, or sleeping colonists, or the first seeds of a second human world. It is one of the most powerful images our species has ever dreamed, and almost every story about the stars begins right here, at the moment of departure. But departure is the wrong place to end the story. It might even be the wrong place to begin worrying, because getting a machine moving fast enough to reach another star is, believe it or not, the part we understand best. We can already sketch the physics. We can already name the fuels. The truly hard question, the one that almost no science fiction story ever stops to ask, is not whether we could throw a spacecraft toward another star. It is whether anything we threw could still be a working spacecraft when it got there. Think about what we are really asking of such a machine. We are asking it to keep functioning, not just existing, but functioning, for a span of time longer than any complex technology humanity has ever kept alive. We are asking it to do this alone, in the coldest and emptiest environment there is, with no mechanic, no spare parts, no rescue, and no way for anyone back home to reach in and fix what breaks. And out there, nothing that breaks ever gets unbroken. Every failure is permanent. Every bit of damage stays. The losses do not reset. They accumulate, year after year after year, for the entire length of the crossing. So before we can ask how long a starship could survive in deep space, we have to be honest about what we even mean by the word starship, and honest about what we mean by the word survive, because both of those words are hiding an enormous amount of trouble. Let us start with the machine itself. What actually makes a spacecraft, an interstellar starship, as opposed to everything else we have ever launched? Here we have to clear away a small confusion, because in recent years the word starship has come to mean something very specific to a lot of people. When many of us hear it now, we picture a gleaming stainless steel rocket built by SpaceX, the enormous vehicle designed to carry people to orbit, to the moon, and eventually toward Mars. That machine is a genuine marvel of engineering, but it is worth being clear about what it is and what it is not. That rocket, and every rocket like it, is a launch vehicle. Its entire job is to climb out of a planet's gravity and reach nearby space. It is a way of leaving the ground. It is not, and was never meant to be, a vessel that crosses the gulf between one star and another. When scientists talk about a true interstellar starship, they mean something categorically different, and for the rest of this journey, that is the only meaning we will use. So what is that different thing? An actual interstellar starship is a spacecraft designed to travel from our star system to another one, and to still be capable of doing something useful when it arrives. That last clause is the whole game, not just to leave, not just to drift in the right direction, but to cross the distance and arrive as a machine that can still perform its purpose. Whether that purpose is to take measurements, to send home a signal, to release a probe, or to carry living passengers safely to a new world. And the distance it has to cross is almost impossible to feel in your body. The nearest star system to our own, Alpha Centauri, sits roughly 4 1/3 light-years away. Proxima Centauri, the closest single star, is about 4 1/4 light-years from here. A light-year is the distance light travels in a year, and light is the fastest thing that exists, moving at about 300,000 kilometers every single second. Light itself needs more than 4 years to make this trip. Nothing we have ever built comes remotely close to the speed of light. So for us, that same crossing is not a matter of years. It is a matter of many thousands of them. To understand just how vast that gap is, we do not have to imagine anything. We already have a machine out there doing the closest thing to it. Its name is Voyager 1. Voyager 1 launched in 1977 alongside its twin, Voyager 2. They were built for a 5-year mission, a quick tour past Jupiter and Saturn, and then, for one of them, onward past Uranus and Neptune. That was the plan. 5 years. Instead, nearly 50 years later, both spacecraft are still alive, still whispering data back to Earth. Voyager 1 is now more than 25 billion kilometers away, the most distant object human beings have ever made. In 2012, it crossed out of the Sun's protective bubble and into true interstellar space. Voyager 2 followed in 2018. By any reasonable standard, these two probes are the most durable, longest-lived machines our civilization has ever sent anywhere. They are, in a sense, our current champions of survival. And yet, and this is the part that should stop you, the Voyagers are not interstellar starships. They are not even close. They were never designed to reach another star, and they never will. Voyager 1 is moving at about 61,000 kilometers per hour, which sounds staggering, and is... But if you aimed it directly at the nearest star, it would need something on the order of 70,000 years to get there. 70,000 years. That is longer than our entire recorded history many times over. Longer than the span since human beings first painted on cave walls. Our single greatest feat of spacecraft endurance would still be in transit long after everyone alive today, and their languages and their nations had turned to dust. So Voyager teaches us two lessons at once, and they point in opposite directions. The first lesson is hopeful. A well-built machine, powered by the slow decay of plutonium, can keep working for half a century in deep space, far beyond anything its designers promised. That is genuinely encouraging. But the second lesson is sobering. Even their champion is nowhere near fast enough, and nowhere near long-lived enough to make an actual interstellar crossing. A real starship would have to do what Voyager does, only better and for vastly longer and while going enormously faster. Which brings us to a fork in the road, a choice that shapes everything else about the problem. There are, broadly, two ways to cross that impossible distance, and each one trades one kind of danger for another. The first way is to go slow. Slow, at least, by the standards of light. You build a ship that travels at some modest fraction of light speed, and you simply accept that the journey will take a very long time. Put real numbers on it, and the weight of the choice lands. A ship cruising at 1% of light speed, 3,000 kilometers every second, more than 100 times faster than any probe we fly today, would still need something like 450 years to reach the nearest star. Push it to 10% of light speed, a truly ferocious velocity we have no idea how to achieve, and the trip still runs past 40 years. In this version, the ship might carry generations of people, or sleeping crews, or nothing but patient machines. The advantage is that a slower ship faces gentler collisions with the stray matter floating between the stars. The catastrophic price of this choice is time. Every single system on board, every circuit, every seal, every pump, every line of code has to keep working not for years but for lifetimes, with no one to replace it. This is not idle daydreaming. Serious engineers have sat down and designed such ships in detail. In the 1970s, a team at the British Interplanetary Society drew up Project Daedalus, a colossal uncrewed probe driven by nuclear fusion, meant to reach a nearby star within a single human lifetime. Decades later, a follow-on effort called Project Icarus reworked the same idea with modern knowledge. And earlier still, Project Orion imagined a ship literally pushed along by a string of nuclear explosions detonated behind it. Each of these is a different embodiment of the same brutal trade between speed and endurance. And here is a detail from Daedalus worth holding on to, because it will matter enormously later. That ship was never designed to stop. It was built to scream past its target at full speed, gathering what data it could in the few frantic hours of the encounter, and then continue on into the dark forever. Even our most careful designers, faced with the real physics, quietly gave up on arriving in the fullest sense, a decision we will have to reckon with before this is over. The second way is to go fast, really fast. There is a well-known research effort called Breakthrough Starshot that has studied sending a tiny, gram-scale probe up to about 20% of the speed of light, around 60,000 kilometers every second, pushed not by fuel it carries, but by a giant laser firing from home. At that speed, the trip to Alpha Centauri would take only about 20 years rather than millennia. This is a candidate concept, not a confirmed mission. Nothing like it has ever flown, and enormous engineering problems remain unsolved. But it captures the appeal of speed perfectly. Shorten the journey, and you shorten the time your machine has to survive. And do not let the word tiny fool you into thinking such a thing would be easy. Even that gram-scale chip, a probe you could balance on a fingertip, weighing about as much as a paperclip, would demand a burst of energy on a scale that beggars belief. The laser array proposed to push it would need to deliver something like 100 billion watts in a brief, blinding pulse, comparable, for those few minutes, to the combined output of 100 large power plants, all of it focused onto a sail thinner than a sheet of paper. That is the price of hurling a paperclip to a fifth of light speed. Now imagine scaling that up to a ship massive enough to carry a reactor, a thick shield, a hold full of instruments, or a living, breathing crew. The energy required does not grow gently as the ship grows heavier. It explodes, because every extra gram must be flung to that same ferocious speed, and then, if it is ever to stop, slowed back down again. This is the first hint of a vice we will meet again and again throughout this story. The cruel fact that the very things which help a ship survive, more shielding, more fuel, more redundancy, more crew, are the same things that make it monstrously harder to move at all. Speed and survival are not partners. They are rivals, fighting over every kilogram. Here, though, is the cruel twist that runs underneath this entire story. Going faster does not simply make the problem easier. It trades a long, slow danger for a sudden, violent one. Because the faster you move through the thin material floating between the stars, the more destructive every tiny piece of it becomes. A speck of dust that would be harmless if you drifted past it becomes, at a fifth of light speed, a projectile carrying the energy of an explosion. So the slow ship must survive time, and the fast ship must survive impact. And there is no third option that avoids both. Every real starship design lives somewhere on that painful trade, choosing which enemy to fight. There is one more twist to the speed question, and it is the strangest of all, because it involves time itself bending. Once a ship approaches a truly large fraction of light speed, the physics of relativity begins to warp the clocks on board. Time on the ship slows down relative to time on Earth. A crew traveling near the speed of light would experience the passage of only a few years, while decades or centuries flowed past back home. In principle, this is a gift to the survival problem. If the ship's own clocks run slow, then its own aging runs slow too, and it needs to endure less of its own time to make the crossing. But two hard truths pin that gift firmly to the ground. First, this effect only becomes powerful at speeds far beyond anything we can currently imagine building. At a fifth of light speed, the slowing of time is only a couple of percent, almost nothing. And second, even where it does help, it helps only the ship's inner clock. It does not reduce the amount of interstellar matter the ship must plow through to cross a given distance. The gas and dust waiting along the route do not care how slow the ship's clock runs. Over a light year of travel, the ship sweeps up the same amount of them either way. So relativity might, in some far future design, ease the ship's aging, while doing nothing whatsoever to spare its skin from the sea it must cross. Even time dilation buys you only half the ticket. But notice something we have been circling this whole time. We keep using the word survive as if its meaning were obvious. It is not. And getting it wrong is the single most common mistake people make when they think about starships. When most of us imagine a starship surviving its journey, we imagine the whole. We imagine the ship not being destroyed, not being shattered by a collision or ripped apart by some cosmic force. And that image is not wrong exactly. It is just wildly incomplete. Because a starship is not a rock. It is not a monument. It is a machine. And a machine can fail in 1,000 ways that leave its body completely intact. So let us be precise, because this precision is the backbone of everything that follows. For a spacecraft, survival is not one thing. It is at least 5 separate things stacked on top of each other, and a real starship has to hold on to all 5 at once. The first standard is the simplest: intact. The ship has to physically hold together. Its structure, its whole, Its frame, none of it can be crushed, cracked open, or eroded away. This is the survival most people picture, and it is real, but it is only the floor, not the ceiling. The second standard is powered. A starship without electricity is not a starship. It is a very expensive fossil. Every other function depends on power. The sensors, the computers, the heaters that keep the whole machine from freezing solid, the transmitter that speaks to home. A ship can be perfectly intact, its hull flawless, and still be as dead as a stone the moment its power runs out. Physical wholeness does not keep the lights on. The third standard is navigable. The ship has to know where it is and be able to change where it is going. Across light years of travel, even a microscopic error in aim compounds into a miss of astronomical size. A starship must be able to see where it is pointed, calculate its course, and nudge itself back on target, again and again for the entire crossing. A ship that can no longer steer is a ship that will sail right past the star it spent centuries trying to reach. The fourth standard is habitable, or in the case of a robotic mission, payload safe. If there are living passengers, the ship has to keep them alive. Air, water, food, warmth, protection from radiation for the whole journey. If instead the ship carries delicate instruments or stored genetic material or frozen embryos, it has to keep that cargo intact and undamaged. This is a wholly separate problem from keeping the hull together. You can have a perfectly sound ship full of dead crew or ruined cargo. And the fifth standard, the one that ties all the others together, is mission capable. When the ship arrives, can it still do the thing it came to do? Can it slow down, look around, gather what it came for, and tell someone? A starship can be intact and powered and on course and still arrive utterly unable to complete its purpose, like a messenger who runs the entire marathon and collapses one step before delivering the message, the words still locked inside a body that can no longer speak. Hold those 5 in your mind, because here's the idea that reframes the entire question. Physical existence is not the same as operational survival. A starship can lose any one of those 5 capabilities and keep every other one. It can be whole but dead, powered but blind, alive but lost. And most unsettling of all, it can lose these things not in a single dramatic disaster, but slowly, quietly, one at a time, while the ship itself keeps sailing calmly onward, still perfectly on course, still physically present and less of a spacecraft with every passing year. That is the real question buried inside this whole subject. Not can we build a ship that goes fast enough, but can we build a ship that stays a ship, that holds all 5 of those threads together across a span of time that dwarfs the working life of anything we have ever made? And here a reasonable objection rises, the one an engineer would raise first. Surely we would not simply build such a machine and fling it at another star on our very first attempt. Surely we would test it, fly it, prove it, learn from its failures and try again, the way we test every other thing we build. It is a fair thought, and it runs straight into a wall that has no door in it, because you cannot meaningfully rehearse an interstellar voyage. A test flight lasting 10 years inside our own solar system would tell you almost nothing about how a machine behaves after 500 years, because the one thing you most need to prove, that the ship can endure a stretch of time longer than any machine has ever endured, is precisely the thing a short test can never show you. You can artificially age a single component in a laboratory, bake it and freeze it and bombard it, but you cannot reproduce centuries of radiation and thermal cycling and mechanical wear and software drift, all acting together on a whole integrated ship in the real interstellar medium, because that combined, compounding, decades-deep punishment is the mission itself. And every long-lived spacecraft we have ever flown, every probe that beat its lifespan by decades, did so with Earth watching over its shoulder the entire time. Sending fixes, working around failures, nursing it through crises. A true starship, deep between the stars, would have none of that. There is no dress rehearsal for a 1,000-year journey. The Starship is that rare and frightening kind of machine that must work correctly the very first time it is ever truly used. At full scale, across a span of time and distance it has never once been tested against. And if it fails out there, it fails alone in the dark, where no one will ever even learn exactly what went wrong. And there is a deeper version of that loneliness, one that reaches past the ship and touches the people who sent it. We have been talking about the machine outlasting its own parts, but a true starship on a long crossing would also have to outlast almost everything that built it. Think about the timescales, honestly. 1,000-year voyage is longer than most nations have ever existed. It is longer than almost any language has stayed recognizable, longer than nearly every government, every institution, every company that has ever kept careful records. The space agency that launches the ship will not be there to greet it. Neither, most likely, will the country that funded it, nor the language its instructions were written in, nor the particular understanding of physics its designers relied upon. Even the great antennas built to listen for the ship's faint voice, the ground stations, the dishes, the patient teams tending them, may crumble and fall silent centuries before the ship has anything to report. This is a strange and sobering kind of fragility, one that has nothing to do with dust or radiation. A starship does not only have to survive the journey, it has to survive the forgetting. It may arrive at its destination in perfect health and find that there is no one left listening, no one who still remembers why it was sent, no one who could even read the message if it managed to send one home. To launch a true starship is to make a promise across a gulf of time so wide that the promise may outlive the ones who made it. And a machine still faithfully carrying out a mission that its makers have long since forgotten is its own quiet kind of ghost. And if you want to know just how strange and how long these interstellar crossings really are, you do not have to imagine a spacecraft at all. Nature has already sent us examples. They are called interstellar objects, chunks of rock and ice that formed around other stars, were flung out into the galaxy, and eventually came drifting through our own neighborhood. And in the last few years, we have finally started catching them in the act. The most recent, and in some ways the most revealing, arrived in 2025. On July 1st of that year, a survey telescope in Chile spotted a faint moving point of light, and within days, astronomers realized it was something extraordinary. Its path through space was not a closed loop around our sun like the orbits of planets and ordinary comets. It was an open, hyperbolic trajectory, the signature of an object that came from somewhere else entirely and is only passing through. They named it 3I Atlas, and it became just the third confirmed interstellar visitor ever found, after Oumuamua in 2017 and Borisov in 2019. What makes 3I Atlas such a perfect teacher for us is not what it is made of, but how it moves and where it has been. It came screaming into our solar system at nearly 60 kilometers per second relative to the sun, a velocity so high that our star's gravity could never capture it. It swung past its closest approach in late 2025 and is now on its way back out, leaving forever, never to return. It appeared, crossed through, and departed, all within a window of months. Blink, and the encounter of a lifetime is over. And here's the detail that should send a chill down your spine when you think about starships. Before it reached us, 3I Atlas had almost certainly spent an enormous stretch of time, possibly billions of years, drifting through the empty space between the stars, held the entire time at a temperature colder than about 10 degrees above absolute zero. Billions of years in the deep freeze of interstellar space, untouched, unheated, barely changed. That is the environment a starship has to cross. That is the medium. Nature keeps its travelers in that cold, silent dark for eons, and it does not care whether they arrive as anything but rubble. Now, a comet does not have to worry about keeping its power on, or steering, or protecting a crew. It is just a rock. It has already surrendered every one of our 5 standards. It was never a spacecraft to begin with, but that is exactly the point. Objects like 3I Atlas show us that the crossing is survivable in the crudest sense. Matter can and does make the trip between stars intact. A lump of ice and dust can travel for billions of years and still be a lump of ice and dust at the far end. The question is whether a machine, a fragile, complicated, power-hungry, information-rich machine, could do the same and still be a machine when it emerged. Nature proves the trip is possible for a rock. It says nothing about whether it is possible for a working starship. And the gap between what a rock can endure and what a machine must endure is where the entire danger lives. Because here is what we have established, and it is a heavier conclusion than it first appears. The leaving, the part we always imagine, the triumphant departure, is in many ways the least of it. We know roughly how to accelerate a spacecraft. What we do not yet know how to do is build a machine that can hold all 5 threads of survival together across thousands of years, or across a violent sprint at 1/5 of light speed, with no help of any kind reaching it from home. The Starship's true enemy is not the launch. It is the journey, every quiet, cumulative, irreversible moment of it. So the moment we stop imagining the ship leaving and start imagining the ship crossing, everything changes. That silent, coasting machine we pictured at the very beginning, engines dark, gliding towards a distant sun, is not resting. It is under attack. From the instant it enters the space between the stars, something begins working against it, patiently, relentlessly, from the outside in. And the first thing you have to understand about that attack is this: the space between the stars is not empty. It only looks empty. In truth, it's a thin, invisible sea of gas and dust and radiation. And our ship is about to plunge into it at a speed that turns even a single atom into a weapon. For the entire length of the crossing, that sea will scrape at the hull, bury itself in the ship's skin, and rain high-energy particles through everything inside. It has been waiting out there the whole time. Let us step outside the ship, into that dark, and see exactly what is coming for it. Step outside the ship. Imagine you could stand on the hull as it coasts, engines dark, through the space between the stars. Look around and you would swear you were standing in a perfect vacuum. An emptiness so complete that the nearest atom seems impossibly far away. And in a sense, that is true. If you scooped up a single cubic centimeter of the space our ship is crossing, a little box the size of a sugar cube, you might find only about one atom inside it. One. Compare that to the same sugar cube of air around you right now, which holds something like 10 billion atoms, and the space between the stars looks like nothing at all. But nothing is exactly the wrong word, and understanding why is the key to everything that follows. Because our ship is not sitting still in that thin sea, it is tearing through it, and when you move fast enough, even the thinnest sea in the universe becomes a storm. Here is the shift you have to make in your mind. It is not the density of the interstellar medium that matters. It is the density multiplied by the speed and the distance. A swimmer gliding slowly through calm water barely feels it, but drive a boat through that same water at enormous speed and the surface turns hard as concrete. Our starship is not drifting through the thin gas and dust between the stars. It is slamming into that material, atom by atom, grain by grain, for years or centuries or millennia, without pause. And every one of those tiny collisions leaves a mark that never heals. So let us meet the three faces of this invisible sea, in the order the ship will feel them: the radiation, the gas, and the dust. Each one attacks the ship in a different way, and each one has been waiting out there the entire time. Start with the radiation, because it is the one enemy that would find the ship, even if it stood perfectly still. The galaxy is filled with what astronomers call cosmic rays. The name makes them sound like beams of light, but they are not light at all. They are particles, mostly the bare nuclei of atoms, protons, and heavier fragments, hurled outward by exploding stars and other violent events, and accelerated to almost the speed of light. They come from every direction at once, a constant, invisible rain that sleets through everything. Right now, as you hear this, a few of them are passing harmlessly through your body. On the surface of Earth, we are shielded from the worst of them by our atmosphere and our planet's magnetic field. Two forms of protection our starship will leave far behind. Out in the open, between the stars, there is no atmosphere and no magnetic shield. The ship takes the full force of that rain, unfiltered, for the whole journey. What does that rain actually do? To the ship's structure, each individual strike is minuscule, but they add up. A high-energy particle plows into the solid material of the hull and knocks atoms out of their places, one at a time, leaving behind microscopic scars. Do this for long enough, and materials grow brittle, discolored, weaker than they were, changed at the level of their crystal structure. Metals fatigue, plastics and polymers stiffen and crack. Slowly, invisibly, the very substance of the ship is being rearranged from the inside. But the structure is not even the most fragile target. The electronics are. Modern computer chips work by controlling almost unimaginably small amounts of electric charge in almost unimaginably small spaces. A single cosmic ray, striking at the wrong moment in the wrong place, can dump enough energy to flip a bit. To turn a 0 into a 1, a yes into a no, inside the ship's computers. Engineers call these single event upsets, and near Earth, they are rare enough to design around. Out in the deep, under a relentless downpour with no atmosphere to soften it, they become a constant hazard. A flipped bit at the wrong instant can crash a program, corrupt a command, or send a healthy system spiraling into confusion. And the same rain that flips those bits can also, over years, physically wear the transistors down until the chips that were meant to think for the ship begin to make mistakes. And there is one more victim of the radiation that people almost always forget: information itself. A starship carries not just machinery, but memory. It's navigation data, it's stored instructions, and perhaps, if the mission is grand enough, the digitized blueprints of life, genetic codes, or the frozen cells of a crew that hopes one day to wake. All of that is stored physically in matter, and matter is exactly what cosmic rays corrupt. Over a long enough journey, the very files that tell the ship who it is and where it is going can decay. One flipped bit at a time, like a book left out in a rain that never stops. Its letters slowly smearing until whole pages can no longer be read. That is the radiation, and it would attack a motionless ship. Now add the ship's speed and meet the second face of the sea, the gas. Remember that thin scattering of atoms, roughly one to a sugar cube of space. Most of them are hydrogen, the lightest and simplest element there is, with a little helium mixed in. Standing still, you would never notice them. But our ship is not standing still. Consider the fast option we described earlier. A vessel crossing at about a fifth of the speed of light. 60,000 kilometers every second. At that velocity, the ship is not passing through the hydrogen. It is smashing into it. From the ship's point of view, it is not moving through a calm gas at all. It is facing a hurricane of atoms blasting into its leading edge at a fifth of light speed, hour after hour, year after year. And each of those atoms, tiny as it is, carries a startling amount of energy at that speed. When a relativistic hydrogen or helium atom strikes the ship's forward hull, it does not simply bounce off. It buries itself, driving deep into the material and lodging there. Now multiply that by the countless trillions of atoms the ship sweeps up along its path. Researchers who have modeled this as a leading hypothesis, not a measured certainty since no ship has ever flown to test it, describe something genuinely alarming happening to the ship's skin. The implanted atoms pile up inside the surface layer. They gather into microscopic bubbles beneath the hull's face. Those bubbles swell and then rupture, tearing away flakes of material in a process the researchers call blistering and exfoliation. The ship's leading edge is, in effect, being made to peel, cooked and cracked and shed from within by the very gas it is flying through. The precise depth of this damage depends heavily on what the hull is made of. The same studies suggest that on the path to Alpha Centauri, the gas bombardment might eat into the surface of a quartz-like material to a depth of roughly 1/10 of a millimeter, while a tougher material like graphite would resist it far better. Those are small numbers, but they are not zero, and small numbers, repeated over light years, are how starships die. There is a second, subtler thing that streaming gas does to the ship, and it belongs to a completely different family of failure. As the hull plows through the thin interstellar plasma, gas so energetic that its atoms have been stripped of some of their electrons, the ship begins to accumulate electric charge on its skin, like a person shuffling across a carpet on a dry day. A charged ship is not a neutral one. It begins to feel electromagnetic forces from the faint magnetic fields threading the galaxy. Gentle tugs and torques acting across its whole body. Forces that have nothing to do with impact or erosion at all. For a feather-light probe, these forces could be enough to nudge it off course or set it slowly tumbling, spoiling the careful aim it needs to survive. It is a strange thought. The ship can be pushed around by the very emptiness it is crossing, not struck, but electrically leaned upon, quietly, for the whole journey. Which brings us to the third and most violent face of the sea, the dust. Scattered through the thin gas, far rarer than the hydrogen atoms but far heavier, are grains of interstellar dust, tiny motes of carbon and silicate, most of them so small you could never see one. A typical grain has a mass measured in fractions of a trillionth of a gram. Individually, they are almost nothing. But the ship meets them at the same terrible speed it meets the gas. And here the arithmetic turns frightening. When our fast ship strikes even a microscopic dust grain, the grain does not scratch the hull the way a pebble scratches paint. It detonates. At a fifth of light speed, the collision releases so much energy so suddenly that the grain and a little pocket of the hull with it simply vaporizes, a flash of superheated material blasted off the surface, leaving behind a tiny crater. This happens over and over, all across the ship's leading face. It is the cosmic equivalent of sandblasting, not one blow, but an unending shower of microscopic explosions, each one carving away a little more of the ship's forward armor. We can even estimate how fast that armor wears down. The same research suggests that a ship moving at a fifth of light speed on the trip to Alpha Centauri might lose about 0.5 millimeter of surface from dust erosion alone. Scale that up, and you find that the ship sheds roughly 1 millimeter of material for every 4 light years it travels. That gives us a haunting rule of thumb. To wear away a full meter of solid shielding, a ship would have to cross something like 4,000 light years. For the nearest star, 4 light years away, that sounds survivable. But it tells you something profound about the deeper voyages. A ship bound for a distant part of the galaxy is not just traveling farther, it is being ground down the entire way. Like a stone dragged across a whetstone that stretches on for thousands of light years. And that steady sandblasting is not even the worst of it. That is the erosion you can plan for, budget for, average out. The nightmare is the rare grain. The one in a countless number that happens to be far larger than the rest. Most dust motes weigh a fraction of a trillionth of a gram, but some are far bigger, and if the ship, on its long crossing, should happen to run headlong into a single grain weighing as much as a full gram, a speck you could just barely see, smaller than a grain of sand, the energy of that one impact at a fifth of light speed would be comparable to a few 100 tons of high explosive detonating against the hull. 1 grain, 1 instant. Enough to gut a spacecraft. This is why we have to be careful never to imagine that a starship faces only one dramatic collision, one single roll of the dice. That is the storybook version, and it is misleading. The truth is layered and worse. There is the slow, guaranteed grinding of the gas and the microscopic dust, which the ship suffers every second of every year. And there is the separate, unpredictable threat of the rare large grain, which might never come or might come on the very first day. The ship has to survive both the endless sanding and the lurking single blow, and no amount of surviving one protects it from the other. And here is a stranger consequence of all that vaporizing, one that turns the ship into its own tormentor. When a grain detonates against the leading edge and blasts a puff of superheated material off the hull, that vaporized matter does not simply vanish. It hangs in front of the ship, a faint, glowing haze of the ship's own shredded substance, torn loose atoms and fragments hurled forward and outward from thousands of tiny impacts. And the ship, moving at a fifth of light speed, immediately flies straight into it. In effect, the fast starship generates its own thin weather at the bow, a hot, ionized cushion of debris that it makes, and then must plow through, moment after moment, a self-inflicted fog of its own erosion. It is a small effect beside the storm of gas and dust, but it is a telling one, because it captures something essential about this whole environment. At interstellar speed, even the act of being damaged damages you further. The wreckage of each collision becomes part of the sea the ship must cross. Nothing the void does to the ship is ever quite finished. Every wound feeds the next. And here is a fact that makes all of this worse, and that most people never consider. The sea is not the same everywhere. We have been picturing the interstellar medium as one smooth, uniform ocean of constant thinness. It is not. Our solar system happens to sit inside an unusually empty pocket of the galaxy, a region so sparse that astronomers call it the local bubble, and just beyond it drift thin wisps of gas we are only now passing through. But the galaxy is full of clouds, vast regions where the gas and dust are packed far more densely than the average, sometimes hundreds or even thousands of times more densely. A starship on a long voyage cannot be sure its whole route runs through the calm. It may sail out of the thin dark and straight into one of these denser clouds. And the moment it does, everything we have described intensifies at once. The erosion, the bombardment, the impact risk, the self-made fog at the bow, all multiplied, with no warning and no way to steer around a fog that spans light years. The ship's worst stretch of road might be waiting somewhere in the middle, invisible until it is already inside it. You cannot budget perfectly for a sea whose depth you cannot chart in advance. And there is one place along the route where the sea is guaranteed to turn against the ship, and it is the cruelest place of all, the very end. We have spent all this time picturing the crossing as a passage through cold and dark, and for almost its entire length, that is exactly what it is. But the destination is a star, and a star is the opposite of cold and dark. As the ship nears its target, the environment does not simply stay the same until it arrives. It inverts. After centuries of drifting through near-perfect emptiness, the ship comes sweeping into a region flooded with fierce light, blasted by the outflowing wind of charged particles that every star pours into space, and most dangerous of all, thick with far more dust and debris than the thin interstellar medium ever held. Every star that has planets also has the rubble of planet-making around it. Belts of asteroids, clouds of comets, rings and streams of dust, far denser than anything the ship met in the deep. So the final stretch of the journey, the last approach to the very world the ship crossed the galaxy to reach, may be the single most hazardous leg of the entire crossing. And it arrives at the worst possible moment, when the ship is at its most worn, its armor thinnest, its systems oldest, its reserves nearly spent. The ship must run the most crowded, most violent part of the gauntlet at the very end, in its most fragile state, with the finish line agonizingly in sight. The dark was patient, the destination is not. Now step back and look at what the ship's own speed has done to it, because here the deep trade-off of interstellar travel finally comes into focus. Go slow, and you soften every one of these blows. A ship crossing at a small fraction of light speed meets the same gas and the same dust, but each collision carries a fraction of the energy. The gas no longer buries itself and peels the hull. The dust no longer detonates, it merely bumps. The violent, explosive face of the sea grows gentle. But you have not escaped the sea. You have simply traded a fast death for a slow one, because now the ship must endure everything else, the radiation and the wear and the aging, for centuries or millennia instead of decades. Go fast, and you flip the trade. Now the journey is short, the ship spends far less total time being rained on, worn down, and irradiated. But the price is that every atom and every grain now hits like a weapon, and the faster you go, the harder they hit. Speed is not a way out of the danger. It is a way of choosing which danger will try to kill you. There is no setting on that dial that makes both threats disappear. And this is the exact point where the ship's designers face their cruelest problem, the one that shapes the entire machine: shielding. The obvious answer to all of this, the radiation, the gas, the dust, is armor. Put a thick shield on the front of the ship, a sacrificial slab of material meant to be eroded and cratered and irradiated, so that the delicate things behind it stay safe. Let the leading edge take the beating. Some proposed designs do exactly this, shaping the ship like a needle so that only a small forward face meets the storm, or placing a block of shielding well ahead of the ship to absorb the impacts before they reach anything vital. This is a sound idea, and every serious Starship concept includes some version of it. But shielding is not free, and its cost is the deepest constraint in the whole field. Because every kilogram of armor you add to the front of the ship is a kilogram you must first accelerate up to interstellar speed, and later, if you ever want to arrive rather than just fly past, a kilogram you must slow back down again. The more you shield, the heavier the ship. The heavier the ship, the more energy it takes to push it to speed, and the more energy it takes to break it at the far end. At some point, the shield you added to survive the journey has made the ship too massive to launch or too massive to stop. This is the vice every starship lives inside. Protect the ship and you weigh it down. Lighten the ship and you expose it. There is no thickness of armor that is simply correct. There is only a painful compromise, chosen in advance, that the ship must then live or die by, because once it is flying, no one can ever add more. And here is the trap that lurks inside the very idea of armor, the thing that makes the vise even tighter. Against dust and gas, a thicker shield genuinely helps. But against the most energetic cosmic rays, piling on more material can actually make things worse. When one of those ultra-high energy particles slams into a thick slab of shielding, it does not simply stop. It shatters the atoms it hits, and each shattering flings out a spray of new, lower energy particles, a burst of secondary shrapnel blasting deeper into the ship. Add too much armor, and instead of blocking the radiation, you have built a machine for turning one incoming particle into a shower of many, raining down on whatever sits behind the shield. Engineers call these secondary showers, and they mean there is a cruel middle ground where more protection buys you more harm. The ship's designers cannot simply keep stacking on armor until they feel safe. Past a certain point, the shield turns traitor. And you cannot armor everything anyway. You can shield the leading face against the head-on storm, but the ship is not a solid brick. It has sensors that must see out, radiators that must face the cold, antennas that must be exposed to speak home. Every one of those necessary openings is a place the armor cannot fully cover. A soft spot in the ship's defenses that the sea can still reach. Which leads us finally to the last face of the deep, the one that is not an attacker at all, but that may be just as deadly. The cold. We think of deep space as freezing, and it is in a way that is hard to overstate. far from any star, the background temperature of the universe hovers at only about 2.7 degrees above absolute zero. The coldest anything can be. There is no sunlight worth the name out there to warm the ship. But here is the subtlety that catches people off guard. The greatest thermal danger to a starship is not simply that space is cold. It is that space gives the ship no easy way to manage its own heat at all. On Earth, heat moves around constantly. It rides on the air, flows through water, spreads by touch from one thing to another. That is why a fan cools you and a breeze feels good. But our ship is surrounded by near-perfect vacuum, and vacuum carries no heat. There is no air to blow across a hot component, no fluid to carry warmth away. In space, heat can leave a ship in only one way, by radiating off into the dark as invisible infrared glow. And that is a slow, stubborn process. This creates a strange double bind. On one side, any part of the ship that generates heat, the reactor, the computers, anything drawing power, has nowhere to dump that heat except through radiators, large exposed surfaces whose only job is to glow their warmth away into space. If those radiators are too small, or if they are eroded and damaged by the very sea we have been describing, heat builds up inside the ship with nowhere to go, and systems cook themselves from within. On the other side, the moment a part of the ship stops generating heat, a system switched off to save power, a section left idle, that part begins to plunge toward the killing cold of deep space, and there is nothing to warm it back up. We have already watched this exact danger play out on the most durable machines we have ever flown. Out past the edge of the solar system, the aging Voyager probes have been forced to switch off heaters and instruments one by one to conserve their dwindling power, and the engineers who command them live in constant fear of a single, quiet catastrophe, that some critical part of the spacecraft will grow so cold that its fuel lines freeze solid. If that happens, the ship loses the ability to steer, to point its antenna, to do anything at all, killed not by a collision or an explosion, but simply by the cold creeping in as the warmth runs out. A starship on a journey of centuries would have to walk that same knife edge for the entire crossing, shedding enough heat to keep from overheating, holding enough heat to keep from freezing, with no star to help it, and no one to adjust the balance from home. So this is the sea our coasting ship must cross, not empty at all, but a thin, patient, relentless medium of radiation that scars its electronics and corrupts its memory, of gas that buries itself in the hole, charges its skin and makes it peel, of dust that sandblasts its armor and, on rare terrible occasions, detonates against it like a bomb, of the ship's own shredded skin turned back against it as it flies, of clouds that may thicken without warning, and a destination that turns violently bright at the very end, and of a cold so total that the ship must fight every second just to keep from freezing to death, while never being allowed to overheat. And all of it, every scar and crater and flipped bit and lost degree of warmth, accumulates. None of it heals. The ship enters the deep hole and comes out the far end, if it comes out at all, having been worked on by that sea for the entire length of the journey. But notice what we have really been talking about this whole time. The hull, the leading edge, the outer skin of the ship. We have been standing outside watching the sea attack the ship's surface, and a starship is not its surface. The armor, the shielding, the outer wall, all of that exists to protect something. The 5 threads of survival we named at the start, intact, powered, navigable, safe, and mission capable. Only one of them, the first, lives on the hull. The other four live inside. And here is the unsettling truth we are about to face. Even if the ship's armor holds perfectly, even if not a single grain ever breaks through, even if the cold is held at bay and the hull arrives unscratched, the ship can still die. Because the deadliest enemy of a starship is not waiting outside in the sea at all. It is already on board. It was built into the machine the day it launched, sealed inside behind all that armor, and it needs no dust and no radiation to do its work. It is the ship itself, growing old. It is the ship itself, growing old. Here is the strangest thing about a starship, and the hardest to accept. You could give it a hull that never cracks. You could wrap it in perfect armor that turns away every grain of dust, deflect every cosmic ray, hold the cold at a flawless distance. You could win completely against the entire sea we just crossed, and the ship would still be dying. Because sealed inside that perfect armor, protected from every outside threat, is a machine, and a machine does not need to be attacked to fail. It only needs to run. Every part a starship carries has a lifetime, not a lifetime imposed by the void outside, but one written into it at the factory, the day it was made. A battery can be charged only so many times. A bearing can turn only so many revolutions. A wire can carry current only so long before its own atoms begin to wander. A line of software can run flawlessly for decades, and then meet for the first time the one situation its writers never imagined. On Earth, we never notice these limits, because we replace things. The phone is upgraded, the car is serviced, the failing part is swapped for a new one from a shelf somewhere. The entire modern world rests quietly on the assumption that when something wears out, a replacement is nearby. A starship is the one place in the universe where that assumption is simply not true. There is no shelf, there is no service, there is no nearby. Whatever the ship launched with is all it will ever have for the entire crossing. And the crossing may last longer than any complex machine humanity has ever kept alive. That is the quiet horror at the center of this whole subject. It is not that space is dangerous, it is that the ship is mortal, and no one can reach it to save it. So let us go inside, past the armor, and watch the machine age. And the first thing to face is the one that everything else depends on: power. A starship without power is not a wounded starship. It is a corpse. Every other function, the computers, the sensors, the heaters holding back the cold, the transmitter reaching home, the systems keeping any crew alive, draws its life from the ship's power supply. So the single most important question about a starship's survival is brutally simple. How long can it keep the electricity flowing? The Voyagers show us both the promise and the problem. They are powered by the slow radioactive decay of plutonium, a lump of it turning heat into electricity with no moving parts at all. One of the most reliable power sources ever built. And yet, even that quiet, dependable source is fading. The particular kind of plutonium the Voyagers carry loses half its potency roughly every 88 years, and so the probes lose about 4 watts of electrical power every single year, relentlessly, whether they use it or not. That is why, after nearly half a century, the engineers have been forced to switch off instrument after instrument, not because those instruments broke, but because there is no longer enough power to run them. The Voyagers are being slowly starved. Their power source is not a tank you can refill. It is a candle, and it has been burning down since the day it was lit. For a true interstellar starship, this problem grows enormously. You might think, why not simply use sunlight, the way so many spacecraft near Earth do? But sunlight is worse than useless out there. The light from a star weakens with the square of your distance from it, so that a ship only a little way past the outer planets already finds the sun too faint to power anything of consequence. And between the stars, in the deep dark our ship is crossing, there is no meaningful sunlight at all. Solar power is a technology of the inner solar system, and the Starship leaves it behind almost immediately. So a real starship, one that must run for centuries and perhaps power a deceleration at the far end, would likely need a nuclear reactor of its own. Fission, splitting heavy atoms, or the far more powerful fusion. Fusing light ones, the same process that lights the stars themselves. Fusion is a candidate, not a solved technology. We have never built a fusion reactor that produces sustained, practical power even here on Earth, let alone one that could run untended for 1,000 years. And here is the cruel part. A reactor is not a candle. It is a complicated machine with fuel that runs down and parts that wear, and it is subject to every other kind of aging we are about to describe. The very thing that keeps the ship alive is itself one more mortal system that can fail. And whatever energy the ship must store between generating and using it, in batteries, in capacitors, degrades too, losing capacity with every cycle and every year, until the storage that was full at launch holds a little less each time it is filled. Now, move from the power to the mind. Because even a ship with power to spare can lose the thing that makes it more than a heater. It's electronics. We talked out in the sea about cosmic rays flipping bits and scarring chips from the outside. But set all of that aside for a moment. Imagine the electronics were perfectly shielded, never touched by a single ray. They would still be dying from the inside, simply by working. This is one of the least appreciated facts in all of engineering. Electronics wear out even when nothing hits them. The chips that think for the ship are made of unimaginably fine structures, wires and gates and layers thinner than anything the eye could resolve. Push electric current through those tiny wires long enough, and the metal atoms themselves begin ever so slowly to drift along with the flow. A process engineers call electromigration, until after years the wire thins in one place and swells in another, and finally fails. The insulating layers that separate one part of a chip from another break down over time under the constant electric strain. The joints of solder that hold components in place crack from the endless expansion and contraction as the ship warms and cools. Capacitors dry out. Memory cells slowly forget, their stored charge leaking away until the data they held becomes unreadable. The ship's own memory of who it is and where it is going, quietly fading. None of this requires an enemy. It is just what happens to electronics as they age, and it happens on a starship exactly as it happens in the drawer where your oldest devices lie dead. Except that on the ship, there is no newer device to replace them, and no factory anywhere within light years to build one. And there is a bitter irony hidden in the ship's own mind. A trade-off that pits 2 of our 5 threads directly against each other. To survive the radiation of deep space, the ship's computers cannot be the fast, delicate chips that power the device in your pocket. Those would be scrambled within weeks. They must instead be radiation hardened, built with older, larger, deliberately crude designs whose very simplicity lets them shrug off the particle rain. This works, and it is how our real spacecraft fly today. but it comes at a price that is easy to miss. A radiation-hardened brain is, almost by definition, a slower and simpler brain. The chips that can survive the journey are often technological generations behind the ones that cannot. So the ship faces an unavoidable bargain. It can carry a swift, clever mind that the void will quickly kill, or a dull, sturdy mind that endures. And a starship, which must think for itself for centuries with no help from home, needs both a mind that lasts and a mind sharp enough to save itself. It cannot fully have both. Every choice to protect the ship's intelligence is also, quietly, a choice to weaken it. And then there is the part of the machine that moves. Anything on the ship that turns, or slides, or opens and closes, a pump circulating coolant, a valve controlling fuel, a wheel spinning to keep the ship pointed the right way, a mechanism unfolding an antenna. Every one of these is a countdown. Moving parts wear against each other. They need lubrication, and lubrication is treacherous in space. Many oils and greases slowly evaporate in vacuum or stiffen into uselessness in the deep cold, leaving surfaces to grind bare metal on bare metal. And there is a stranger danger still. In the perfect vacuum of space, two clean pieces of the same metal pressed together can simply fuse into one, welding themselves shut without any heat at all, because there is no air between them to keep them apart. A mechanism that cold welds is a mechanism that will never move again. Every hinge, every joint, every spinning wheel on the ship is a small clock, ticking down toward a moment when it seizes. And once it seizes, no hand will ever reach in to free it. Even the ship's thoughts can rot in their way. A starship runs on software, and software carries a quiet inheritance of flaws. Some errors lie dormant for years, waiting for the one precise combination of circumstances that will trigger them. Some accumulate slowly, tiny miscalculations building on each other until the ship's understanding of its own state drifts away from the truth. Here on Earth, we hold software together with constant repair. The programs on your devices are patched and corrected again and again, month after month, by people watching for exactly these failures. A starship gets almost none of that. Early in the journey, a fix from home might still reach it, though it would arrive years late, having crawled across the light years. Later, deep in the crossing, no fix comes at all. The ship must find its own faults, understand them, and heal its own code, or slide, degree by degree, into a confusion from which no one can retrieve it. And if the ship carries people, then layered on top of this entire dying machine is a second machine, more fragile still, the one that keeps them breathing. A crewed starship must be a closed world. It cannot open a window. There is nothing outside but vacuum. So it must recycle everything, turn exhaled breath back into fresh air, filthy water back into clean, waste back into the beginnings of food. And it must keep that cycle in perfect balance, not for a mission of days, but for years or lifetimes. We have tried, in the smallest way, to build such a closed world here on Earth, and the results are humbling. In the early 1990s, a sealed habitat called Biosphere 2 enclosed 8 people inside a self-contained ecosystem, meant to sustain itself. Within about 2 years, the balance had failed. The oxygen in the air fell steadily, dangerously, until it had to be pumped in from outside to keep the crew safe. A carefully engineered miniature world, built by experts, tended by a crew whose lives depended on it, right here on a planet where help was a phone call away. and it could not hold its own air in balance for 2 years. Now imagine that same task, but sealed forever, with no outside to pump anything in, for a journey of centuries. Every crop that fails, every leak that whispers away a little air, every unseen shift in the invisible balance of microbes' compounds, because there is no reset and no rescue. And there is a slower, subtler failure waiting inside every closed world, one that has nothing to do with running out and everything to do with building up. A sealed ship cannot throw anything away. Whatever it makes, it keeps. Over years and decades and centuries, the tiny byproducts that an open world simply scatters into the wind and washes into the sea have nowhere to go aboard a starship. And so they gather. Faint chemicals seep out of plastics and paints and adhesives into the sealed air. Substances that were utterly harmless in a single breath and quietly dangerous after 10,000 of them. Minerals precipitate out of endlessly recycled water and crust the insides of pipes, narrowing them year by year until the flow chokes to a trickle. Films of microbes creep across every damp surface, colonizing filters and valves and sensors, changing and spreading as they go, in ways no one can fully predict. On the space stations we fly today, crews spend real, constant effort scrubbing surfaces, wiping down walls, and swapping out fouled filters just to hold this creeping contamination at bay. And they are resupplied from Earth again and again, their worst buildup carried home or vented into space. A starship has no home to carry it to and cannot afford to vent away the very air and water it can never replace. So across a long enough voyage, a closed world faces a danger stranger than starvation. It can slowly poison itself with the residue of its own living, fouling its own lungs and veins with things it can neither expel nor ever fully clean away. The threat is not only that the ship runs empty, it is that the ship, sealed tight against the void, gradually fills up with itself. By now you may be feeling the true shape of the problem. It is not any single failure. It is the arithmetic of many finite lifetimes, all running down at once, inside a machine that cannot be resupplied. And the engineer's only real weapon against that arithmetic has a name: redundancy. Redundancy means carrying more than one of everything that matters, so that when the first pump fails, a second takes its place, and when the second fails, a third. It is how spacecraft survive today, and it works. But redundancy is not a cure. It is a delay, and a costly one. Every backup is more mass to accelerate and someday to slow down. Every backup takes up room and adds complexity. And here is the cruelest catch of all. The backups age too, even sitting idle. The spare pump that has never turned still ages on its shelf. Its seals still stiffen, its metal still creeps toward cold welding, its electronics still rot. You cannot carry an infinite number of spares, and the ones you carry do not stay new. So redundancy buys the ship time, precious, mission-lengthening time, but every failure spends some of that reserve, and the reserve only ever shrinks. It can never be topped up. What the ship's designers pray for then is not that nothing fails. Everything will fail eventually. But that the ship fails gracefully. That systems die one at a time, slowly, each loss absorbed by a backup, the machine gently declining while still doing its job. What they dread is the opposite: cascading failure, where one broken system overloads the next, which trips the one after that, and the losses race through the ship faster than any backup can catch them, until in a matter of hours, a healthy spacecraft becomes a dead one. The whole art of building a starship is the art of arranging its mortality of ensuring the machine comes apart slowly and safely, rather than all at once. But surely, you might think, there must be a way out. Surely a sufficiently clever ship could repair itself. This is the great hope, and it deserves an honest hearing, because there is real substance to it, and real limits. The first idea is autonomous repair. Give the ship robots and intelligence enough to fix its own broken parts, to diagnose a failing system and mend it without any human hand. It is a beautiful idea, but follow it one step further and the flaw drops away. The repair system is itself a machine. The robots have bearings that seize and electronics that rot. The intelligence runs on chips that age and software that drifts. So who repairs the repairer? You can build a system to fix the ship, but then you need a system to fix that system, and a system to fix that one. And at the bottom of every such tower, there is always some final layer that no one is left to mend. Self-repair does not escape the problem of aging. It only moves the problem somewhere deeper inside the ship. The second idea is self-manufacturing. Rather than carrying finished spare parts, carry raw materials and the machinery to make new parts on demand, printing fresh components as the old ones fail. A small factory riding along inside the ship. This is genuinely powerful because a stockpile of raw material can replace a far wider range of broken things than a fixed set of spares ever could. But the factory, too, is a machine that ages, and it adds enormous mass and complexity to a ship that is already fighting for every kilogram, and it can only ever make what it has both the materials and the blueprints for. A ship can carry a workshop into the deep, but a workshop that breaks cannot rebuild itself from nothing. The third idea is modular design. Build the ship so that when any piece fails, a whole module can be swapped out cleanly for a replacement, like changing a cartridge. It helps. It makes the failures the ship does suffer easier to survive. But you still have to carry the modules, and the modules still age, and you can only carry so many. And the fourth idea reaches into the crew itself. Biological dormancy. If living passengers are the most fragile and demanding cargo of all, consuming air and food and water every day, aging with every year, then perhaps you could put them to sleep, freeze them, or slow their bodies to a crawl, so that they neither age nor consume during the long crossing, waking only at the end. In principle, this would lighten the life support burden enormously, and spare the crew the centuries. In practice, this is a speculative idea, not a proven one. We cannot yet safely hold a human being in such a state for even a short time, let alone for hundreds of years. And notice the trap even in the dream. The machinery that keeps the sleepers frozen must itself run flawlessly, powered and cooled and controlled for the entire journey. So you have not removed the dependence on the dying machine. You have made the sleeping crew utterly hostage to it. Every escape route, followed far enough, circles back to the same wall. There is no trick that makes a machine immortal. There is only the endless, careful work of making it last a little longer. And how long it must last depends entirely on what kind of starship we are talking about. Because here the three great archetypes split apart, and their survival problems could hardly be more different. The simplest is the uncrewed probe, a robotic ship, carrying no life, only instruments and a purpose. It has the easiest survival problem of the three because it needs no air, no food, no closed ecosystem. It does not care about comfort or company or the passage of generations. It must only keep its power flowing, its mind working, its course true, its payload safe, and its voice able to reach home. That is hard enough. Everything we have described still applies to it. But a probe has the best odds of arriving in some functional form, even if battered, even if half its systems have gone dark, even if it limps to its destination as a shadow of what left home. For a robotic ship, partial survival can still be success. Harder is the conventional crewed ship, one that carries living people who expect to be awake, and who expect to see the destination with their own eyes. Now every fragility of the machine is joined by the fragilities of the body and the closed world that sustains it. And there is a hard ceiling built into this design. The crew must live long enough to arrive. That confines such a ship to journeys short enough for a human lifetime, which in practice means either a very nearby star or a ship fast enough to make the crossing in decades, with all the violent impact dangers that speed brings. A crewed ship cannot simply take its time. Its passengers are a clock that runs out. And hardest of all, by an enormous margin, is the generation ship, a vessel so vast and so patient that no one who boards it will ever see the end. On a generation ship, the people who launch are meant to live their whole lives aboard, to have children, to grow old and die in transit, so that it is their descendants, generations later, who finally arrive. This is the ultimate test of survival, because now the ship must keep alive not just a machine and not just a crew, but an entire self-sustaining society and ecosystem, unbroken for centuries or millennia. And the demands stack in ways that have nothing to do with engineering at all. Researchers who have modeled such voyages find that the crew cannot be too small, or the community collapses through the slow narrowing of its own bloodlines. One careful study concluded that with strict rules, a starting crew of as few as about 98 might just sustain itself to the nearest star. Others argue that to survive not just the ordinary journey, but any sudden catastrophe along the way, the crew would need to be far larger. One detailed estimate placed the safe range somewhere between roughly 14,000 and 44,000 people. And all of this remains today at the very lowest rung of readiness. Pure mathematics and speculative design, never built, never tested, existing only as equations on a page. The generation ship asked the machine to outlast not merely its own parts, but the memory, the knowledge, and the will of every person who ever knew why the voyage began. And that last point deserves to be drawn all the way out, because it is a kind of failure no armor and no redundancy can ever protect against. On a voyage that spans generations, the people who built the ship do not arrive. They launch and they die along the way, and so do their children and their children's children. The men and women who understood the reactor down to its bones, who knew not merely how to run it, but why every choice had been made, what its quirks were, what a particular sound or silence from it truly meant, are gone within a lifetime or two. Everyone who comes after inherits a machine they did not design and were only ever taught to tend. And knowledge, handed down by living voice and working hand across many generations, thins with every pass. Skills that are not constantly practiced fade. The hard-won reasons behind a procedure are forgotten long before the procedure itself is, until people are dutifully following rules they no longer comprehend, helpless to improvise the moment those rules collide with a situation their ancestors never wrote down. A repair manual can be copied down to the last letter and still be misread by a mind that has lost the deeper context needed to make sense of it. So a generation ship can arrive physically sound, reactor humming, hull unbreached, air still breathable, and fail all the same, because the living understanding required to keep it running, and above all to mend it when it finally falters, has quietly drained out of the crew over the centuries. The metal can outlast the minds that knew how to care for it, and a machine that no one still aboard truly understands is a machine already half lost in the dark, however sound its structure, however faithful its engines. The greatest thing a generation ship must preserve across the void may not be its hardware at all. It may be its own knowledge of itself. So there it is. The enemy inside. Not the dust, not the radiation, not the cold, but the simple, patient mortality of every component, every circuit, every seal, every living cell, and even every hard-won skill, all of them running down at once inside a vessel that cannot be resupplied, repaired from outside, or reached by any rescue. A starship is a race between two clocks, the distance it must cross, and the lifetime of the machine crossing it. And nothing we have described so far guarantees that the machine's clock outlasts the journey. But suppose, against the sea outside and the aging within, against the fading power and the rotting circuits and the seizing gears and the fouling air and the fragile balance of a closed and living world, suppose the ship holds. Suppose it does everything right. It crosses the impossible, dark still powered, still thinking, still whole, still carrying its purpose and its passengers alive. Suppose, after centuries, its destination star swells at last from a point of light into a blazing sun ahead. Then the ship faces the one test it has been saving for the very end. The test that every other system existed to make possible. Because reaching a star and arriving at one are not the same thing. And to arrive, the ship must still be able to see where it is going, to steer, to speak, to protect what it carries, and above all, somehow, to stop. And stopping, it turns out, may be the hardest thing of all. And stopping, it turns out, may be the hardest thing of all. Picture the ship now at the end of everything. It has crossed the impossible dark. It has survived the sea outside and the aging within. Ahead, no longer a faint point among countless others, its destination star burns, a real sun growing brighter every day, close enough now that the ship could almost be said to have arrived. This is the moment that the entire mission was built for, the payoff of centuries. And it is precisely here at the finish line that a starship is most likely to fail in the cruelest way of all. Because we have to say plainly something that sounds like a paradox and is not. Reaching a star and arriving at a star are two completely different achievements. Reaching it means your body arrives at the right place at the right time, that you cross the distance. Arriving means you get there as a working starship, still able to do the thing you came to do, and the gap between those two is where most of the tragedy in this whole story lives. A ship can reach its destination flawlessly and fail to arrive at all. To arrive, truly arrive, the ship must still be able to do 5 things at journey's end, and it must do all of them at once, after centuries of everything trying to take each one away. It must see, it must steer, it must speak, it must protect what it carries, and hardest of all, it must stop. Let us take them in turn and watch how each one can quietly slip away while the ship sails serenely on. Begin with seeing. A starship arrives blind unless its eyes still work. And its eyes are exactly the delicate instruments most exposed to everything we have described. The sensors and cameras and star trackers that must peer out through the hull, out past the armor, into the very sea that has been scouring the ship for the whole crossing. These are the parts that cannot be fully shielded, because a sensor that cannot see out is no sensor at all. So they take the radiation, they take the erosion, their lenses cloud, their detectors fill slowly with the scars of cosmic rays until the image they return is a haze of false signals. Their fine electronics rot like all the rest. A ship can arrive with a perfect hull and a full reactor and be, for all practical purposes, blind, its windows on the universe fogged over by the journey that carried it there. And a blind ship cannot do any of the other four things, because every one of them depends first on knowing where you are. Which brings us to steering. Suppose the ship can still see. It must now do something genuinely difficult and far harder than simply holding a straight line. Think about what the ship is actually aiming at. It is not aiming at where its target star is. It is aiming at where that star will be after the entire crossing, because the star is not standing still. It is moving through the galaxy on its own path. And over the centuries of the journey, it will travel a considerable distance from where it sat at launch. The ship must lead its target the way a hunter leads a bird in flight, launching not at the star, but at an empty patch of space where the star is destined to arrive at the exact moment the ship does. Get that prediction slightly wrong at the start and you spend the whole voyage flying toward a rendezvous that will never happen. And it gets subtler still, because over light years of travel, the tiniest error in aim, an angle so small you could never measure it by eye, swells into a miss of staggering size by the time the ship arrives. A course that was very nearly perfect at launch will not be perfect at the end. The ship has to notice the drift and nudge itself back again and again all the way in. But nudging requires two things that both grow scarce with time. It requires a working brain to calculate the correction, the same aging computers we watched decay earlier, and it requires fuel to actually push. A reserve of propellant that the ship has been carrying and slowly spending for the entire crossing. Run low on either, and the ship loses the ability to steer. And there is a final, eerie difficulty waiting at the very end. The ship must still recognize its destination when it gets close. After centuries of travel, seen from a wholly new angle, with the whole sky rearranged by the ship's own motion, the target system will not look the way it did from home. The ship must be able to pick its star out of a transformed heaven and confirm that this, at last, is the place. And a ship that cannot correct its course, or cannot even be sure which light is the one it came for, will sail past the very world it spent centuries reaching, missing it by a distance larger than the world itself, with nothing left to do about it. Now suppose it can see, and it can steer. It must also speak, because for most missions, a starship that cannot tell anyone what it found has, in a sense, failed no matter how gloriously it succeeded. And speaking across interstellar distance is its own quiet nightmare. The signal the ship sends home is a whisper that must cross light years, spreading and weakening the entire way, until what arrives at Earth is almost lost in the noise of the universe. To be heard at all, the ship needs a powerful transmitter and a large antenna aimed with exquisite precision back the way it came. And both the transmitter and the aiming depend on power and on mechanisms that may have failed. And even if the ship can be heard, there is a further maddening limit. It can barely say anything. The fainter a signal, the slower it must speak to be understood at all, because each scrap of information has to be repeated and stretched and reinforced to survive the crossing. A ship at another star might be able to trickle its discoveries home only a few faint bits at a time, so that the images and measurements it gathered in a few hours of arrival could take months or years to dribble back across the light years. The ship could learn something extraordinary about a new world, and then spend the rest of its dying life trying slowly to finish the sentence. And there is a deeper cruelty in the speaking still, and it is this: even when the ship does speak, no one can answer in time to help. A message from the nearest star takes over 4 years to reach us, and our reply takes over 4 years to return. For more distant targets, the round trip is measured in decades or centuries, so Earth can never truly command a starship. It can never reach in during a crisis and fix what is going wrong. By the time we learn that something has broken, the moment to act passed years ago. By the time our instructions arrive, the ship has long since lived or died on its own. This is perhaps the loneliest fact in all of spaceflight. The ship is not just far away. It is beyond the reach of help, permanently, by the simple law of the speed of light. Whatever happens out there happens alone. And then, if the ship carries anything precious, instruments or genetic material or living, sleeping crew, it must have kept that cargo safe through all of it, and must keep it safe now, at the end. We have already seen how radiation corrupts stored information, and how a closed ecosystem can fail. Arrival does not relieve this burden. If anything, it intensifies it, because now the payload must be not merely preserved, but ready. The sleepers must wake, the instruments must switch on, the frozen seeds of a new world must still be alive. A ship can arrive intact and powered and on course and speaking, and open its hold to find its purpose died somewhere in the dark, quietly, years ago, while everything around it kept working. But all of these, the seeing, the steering, the speaking, the protecting, all of them assume the ship can do the one thing we have saved for last. The thing that is, for many starships, simply the hardest problem in the entire endeavor. It must stop. We almost never think about this. Every story of reaching another star imagines the arrival as the easy part. You get there and there you are. But think about what there you are actually requires. The ship has spent its whole journey building up and holding an enormous speed. To arrive at its destination in any useful sense, to enter the star system, to study a planet, to release a crew onto a new world, it cannot simply blaze straight through at a fifth of the speed of light. At that velocity, it would cross the entire target system in a matter of hours and be gone forever out the other side. Having caught only a blurred glimpse of its destination after traveling for decades to reach it. To actually arrive, the ship must shed all that speed. It must break. And breaking, in the deep truth of physics, is almost exactly as hard as launching was. To feel just how hard, you have to understand the trap that lives inside carrying your own brakes. Suppose the ship plans to slow down by firing an engine, the way a rocket does. Then it must carry the fuel for that braking all the way across the void. But that braking fuel has mass, and to carry extra mass, you had to accelerate it up to cruising speed in the first place, which took still more fuel at launch. And that launch fuel had mass too, which demanded yet more fuel to move it. The costs pile up on top of one another, multiplying rather than adding, until the amount of propellant required to stop a meaningful payload at another star balloons to something monstrous. Far, far more than the payload itself, sometimes more than the ship could ever plausibly carry. This vicious spiral is one of the hardest walls in all of rocketry, and it is the reason that stopping, not going, is what quietly breaks so many Starship dreams. It is such a hard wall that some of our most serious designs simply refuse to climb it. This is the reckoning promised earlier when we met Project Daedalus and its unsettling choice. The fusion probe designed never to stop. Now we can see why its makers surrendered braking. They ran the numbers on carrying enough fuel to slow a real payload, watched the mass spiral toward the impossible, and concluded that the only honest mission was a blazing flyby. Everything gathered in a few frantic hours, then onward into the endless dark. That is a kind of arrival, but a thin and heartbreaking one. A lifetime of travel spent for a single afternoon of looking, and then gone. It forces a bleak admission. For many missions, truly stopping is off the table, and arrival means nothing more than a glimpse in passing. The designs that do hope to stop must reach for tricks that need no fuel, and every one of them is fragile in its own way. Some propose spreading a vast magnetic sail, a great invisible net of magnetic field, and using it to grip the thin plasma of the destination system and drag against it like a parachute opening into a headwind. Others imagine unfurling an enormous physical sail and turning it to catch the light of the target star head-on, letting the star's own glow push back against the incoming ship and gently bleed off its speed. Both are elegant, both might work, but both are delicate, sprawling structures that must survive the entire crossing folded and waiting, and then deploy flawlessly and hold their shape at the one moment they are needed. After centuries of doing nothing but aging in the dark, a parachute you cannot inspect, cannot test, and cannot repair, that must open perfectly on the first and only try at the far end of the longest journey ever made. A ship that cannot break does not crash. It simply does not stop. It flies through its long-sought destination and out into the dark beyond, still moving, still perhaps intact, having reached its star and utterly failed to arrive at it. So now you can see the full and terrible shape of the arrival problem. The ship must, at the very end of the longest and most punishing journey ever attempted, simultaneously see clearly, steer accurately toward a moving target, speak powerfully across the light years, protect what it carries, and shed the greatest speed anything has ever carried, using systems that have been aging and eroding and failing for the entire crossing, with no help able to reach it, and no second chance if any one of them slips away. And there is one last shadow over the arrival, stranger than all the rest, because it is not about the ship at all. It is about the place, everything the mission was built around, the choice of target, the reason for going, the belief that something worth reaching waited at the end, was decided at launch, from what we could glimpse of that far world across the light years, centuries before the ship would ever get there. But a star system is not frozen in place while it waits. In all the time the ship spends crossing, the destination goes on changing, and the ship's knowledge of it is always as old as the journey is long. The crew or the probe is aiming at a world as it appeared generations ago, and can only discover what it has truly become at the very end, when there is no longer any way to turn back. A ship might cross the entire void flawlessly and arrive to find that the planet it was sent to study is not the planet the launch generation believed in. Its promise reassessed, its atmosphere reread. The very thing that made it worth a 1,000-year voyage quietly overturned by discoveries made back home long after the ship went silent and slipped out of reach. This is a failure of a wholly different kind. The machine does everything right. It sees, it steers, it speaks, it protects, it even stops. And still it can arrive at a destination that is no longer the one it was sent to, carrying a purpose that the passing centuries, unknown to anyone aboard, have already hollowed out. There is even a version of this that seems to mock the whole endeavor. Suppose a ship sets out for a distant star on the very best technology of its day. Then, decades later, while it is still only a fraction of the way there, a faster ship is built at home and launched along the same path, and overtakes its own ancestor in the dark, reaching the target first. The first ship, still healthy, still striving, arrives to find the work already done, its data already gathered and sent home, its long and lonely voyage rendered pointless not by any failure of its own, but by the simple march of progress it left behind. It is one of the strangest riddles in all of interstellar travel, that sometimes the wisest move may be to wait and not launch at all, because whatever you can send today may be quietly outrun by whatever you could send tomorrow. A starship can be defeated before it ever arrives, not by the dark and not by decay, but by the patience it did not have. And here at last, we arrive at the true and unsettling heart of everything we have been building toward. Because we have spent this whole journey imagining ways a starship might be destroyed. The grain of dust that detonates, the reactor that fails, the ecosystem that collapses. But the deepest danger of deep space is not destruction at all. Deep space does not need to kill a starship in one spectacular blow. It has a quieter and far stranger weapon, and it is this: the ship can keep going. Consider it carefully, because it is the idea this whole journey exists to reach. A starship can remain physically present, intact, whole, recognizable, long after it has ceased to be a functioning spacecraft. Its hull can hold. Its momentum can carry it, perfectly, exactly on the course it was set, straight toward its destination. And yet, one by one, across the years, the things that made it a starship can slip away in the dark. First to sensor clouds, and the ship sees a little less. Then a backup fails, and its margin for error narrows. Then its stored memory decays, and it forgets a little of what it knew. Then a mechanism seizes, and it can no longer turn to look where it wishes. Then the power sags, and it must let another system go quiet. None of these is a catastrophe. None of them is the dramatic collision we always imagine. Each is small, each is survivable, but each is permanent, and each subtracts from what the ship is, until somewhere in the middle of the void, without any single moment you could point to and call the end, the ship crosses an invisible line. It stops being a spacecraft that is traveling and becomes an object that is merely moving. And the most haunting part is that from the outside, nothing would look wrong. The ship would still be there, still gleaming, still cutting cleanly through the dark toward the star it was aimed at. It might even reach that star, dead on target, precisely on schedule, but it would arrive the way a discarded satellite arrives, as a thing that got somewhere, not as a machine that accomplished something. It would coast into the light of a new sun blind, silent, unable to slow, carrying instruments that no longer work and perhaps a crew that no longer breathes. A perfect monument to a mission that quietly ended somewhere in the years between the stars. The ship would have reached its destination. It would never have arrived. This is what makes the survival of a starship so different from the survival of anything else. It is not a single countdown to a single failure. It is the slow, cumulative loss of capability in a place where every loss is forever and no loss can be undone. The ship does not need to be broken. It only needs to be worn down, one quiet degree at a time, faster than it can hold itself together. And because it can never be repaired from outside, the only question that matters is whether the ship can carry enough life within itself to still be alive when it gets where it is going. Notice too that there is no single answer to how long a starship could survive. No one number, no universal lifespan. We have to resist the temptation to say something clean and final like 1,000 years or 10,000. The truth is more honest and more interesting than that. A starship's survival depends on everything at once, on how fast it travels, which sets whether it faces the slow death of time or the violent death of impact, on what it is made of and how it is shielded, which sets how quickly the sea outside wears it down, on whether it carries robots or sleepers or a living society, which sets how fragile its cargo is and how long it must last, on how much redundancy it carries and how gracefully it fails, on whether it must merely fly past or must somehow stop. Change any one of these, and the answer changes entirely. There is no lifespan of a starship. There is only the lifespan of a particular starship, on a particular journey, with particular choices baked into it at launch. Choices that can never be revised once it is gone. And so we come back, at the very end, to the image we started with. That silent ship, engines dark, gliding across the void toward a distant sun. When we began, it looked like a symbol of escape, of humanity slipping free of its cradle and reaching for another star. And it is that, but we understand it differently now. We know that the coasting is not rest. We know that from the moment it entered the dark, the ship was under siege. From the thin sea outside scouring its skin, and from its own mortal machinery running quietly down within. We know that every scratch and every flipped bit and every seized gear was permanent, and that they were all adding up the whole way. The ship is not resting. It is enduring. It is engaged every second of every year in a struggle it cannot win permanently and can only hope to prolong long enough. A struggle against time itself, against accumulated damage, against the simple irreversibility of everything that goes wrong in a place where nothing can be fixed. And here, finally, is the thought worth carrying away from all of this. We tend to believe that the great challenge of reaching the stars is a challenge of speed and power, of building an engine mighty enough, of going fast enough, of crossing the terrible distance, and those are real challenges. But they may not be the hardest one. The hardest one, it turns out, may not be about motion at all. It may be about permanence. To build a true starship is to build a machine that can remain recognizably itself, powered, aware, capable, alive, for longer than any complex technology our species has ever managed to keep working, in an environment where every failure is final and no help can ever come. We have never built a machine that lasted 1,000 years. We have never built a machine that could fully repair itself. We have never built a closed world that could sustain its own life indefinitely. A starship would have to be all three of these things at once, and it would have to be them alone, in the dark, with no one able to reach it. That is the real measure of the thing. Not how fast we could throw a ship toward another star, but whether we could make a ship that is still a ship when it arrives. Whether we could send something across that unimaginable gulf that reaches the far shore not as a drifting relic, not as an elegant corpse coasting past a world it can no longer perceive, but as a living machine, one that can still open its eyes, and look at the new sun it has finally reached and know that it is there. Because in the end, the distinction is the whole story. Anything can reach a star, given enough time and a steady enough aim. A stone flung hard enough will get there eventually. The universe is full of objects crossing between the stars, and it does not care whether they arrive as anything but rubble. The question that separates a rock from a starship, the only question, really, that has ever mattered in this entire endeavor, is not whether the thing arrives. It is what arrives, and whether, after all those years in the dark, there is still something there that can answer to the word arrived,